We're going to talk about MA, and then we're going to talk about time. And then we're going to talk about MA and time together in mass. We're going to talk about technique compensations using mass. And again, most of the time, unless we need to affect change in either patient exposure or penetration of very dense objects, most of the time our technique compensation is going to focus around mass. So we'll talk about that, and we'll talk about some hypotheticals the same way that we did with KVP. But again, MA is what controls the filament circuit. You don't have mass until you make your exposure, you apply the KVP, and the electrons travel across the tube. So in prep, the only thing that you have is MA. You've activated the filament circuit or you've increased the current in the filament circuit to heat up those filaments to the point of creation of a space charge and thermionic emissions. And really, the amperage that's going through there at the time is truly amperage. It may not be milliamperage, but what's going to travel across a tube will eventually be MA joined with the time that they travel across the tube to create mass. So the only thing that MA controls is how many electrons that you're going to put on that filament at any given time. It's going to control at exposure how many electrons travel from the cathode to the anode within a specific amount of time. So it truly controls the numbers, MA and eventually mass with time, controls the number of electrons that you send across the tube. You can't really focus the electrons on the atom themselves, so it doesn't change the percentage of electrons that eventually lose enough kinetic energy to become more photons. It's still just a numbers game. So the more numbers that you throw at the target atom, the more X-rays that you create. So we call it intensity. I struggled with it a little bit when I was in school. I wanted to make KVP intensity. To me, it just seemed like intensity equals power. Power is KVP. But that's not how we relate intensity to X-ray exposure. Intensity is just numbers. MA is consistent except for on falling load generators, and I'll tell you to go back to last semester where we talked about falling load generators. You probably have never worked with one of those. If you have, you probably didn't recognize it at the time. They function just like every other control panel. But what happens with a falling load generator is it's a specific type of machine that came out, and I think that the intended application was for like cardiac imaging, where we needed very, very fast exposures as quickly as we could get them. And what it does, a falling load generator, what it does is it starts with the very highest MA. If you're phototiming, it starts with the very highest MA that machine allows. And it makes an exposure off of that until it basically exhausts the space charge that's created at that MA station, and then it drops to the next lowest MA station, and so on and so forth. So the purpose for a falling load generator is to get as quick an exposure on every image that you can possibly get. If you work in cardiac cath lab, you might work with a machine like that, but they used to even be in diagnostic departments, but I don't think that you're probably seeing those much anymore. So it's the quantity of electrons, and it directly affects the quantity of the photons. You double your electrons and you double your photons, it doesn't give you any greater likelihood of getting high energy or lower energy X-ray photons. It's kind of like shooting a shotgun. You shoot a shotgun, you throw a lot of shot shell out into the air. If you shoot it twice, you shoot twice as many. So that's basically what mass is just the number of individual electrons that you send, and If you double the number of electrons, you double your number of photons that you create. So it controls filament current. It controls the heating of the filament. Filament current is always present to keep the tube warm, but it's a very low current. So even though the current's there, you're not to the point of thermionic emissions. If you remember, again, the most common cause for tube failure is going to be heat, and how that heat is going to cause failure is different in different components. And we talked about all those last semester. We talked about applying a lot of heat to something that's cold, and what could happen there is you could break it. So if you've got a cold filament and you apply a lot of electrons to it and create thermionic emissions in a great big hurry, you could break the filament. In addition to that, if the tube itself, the entire tube was very cold and the filament survived, and you send those electrons across the tube to bombard the target, then what could happen is the target could crack, right? And then we talked about keeping the heat off of the bearings. We talked about arcing. We talked about all the different things that cause tube failure. But the purpose for keeping a current going through the filament is really to keep the tube warm so we don't put a big exposure on a cold anode and crack the anode. So the heating of the filament increases whenever we get to the prep stage. We press the prep button and we increase the amperage to the filament, and we get to the point of creating a space charge. That's what we call thermionic emissions. Again, thermionic emissions just means hot ions, and these are electrons, so they're ions, and they get so hot that they congregate on and around the filament itself. So that occurs during prep stage. Whenever you hit prep, what happens is those electromagnets that are outside of the X-ray tube but inside of the housing, you remember they're what we call the stators. They're outside of the X-ray tube, but they're still considered to be a part of the X-ray tube. So they fire in order, and that makes the anode rotate. So that happens, and at the same time we get this creation of a space charge, thermionic emissions. Once we hit our exposure, then we've actually got mass. Before we hit our exposure, the only thing that we have is MA. Mass is a measure of two things. One is the number of electrons that travel across the tube, and the length of time with which they travel across the tube. So if we increase our MA or we increase our time, it doesn't matter which one, if we double either one of those two, then what we're going to do is directly double the number of electrons we send across the tube, and that directly doubles the number of photons that we create. So there's a direct control there. It directly controls the number of photons that we create because it directly controls the number of electrons that we send. So an amp, remember, is 1 coulomb flowing through a circuit per second. And a coulomb is a lot of electrons. So just kind of breaking it down, it would focus so much on how inefficient X-ray creation is. We say that maybe 80 kVp, and even less so at lower kVps, but the likelihood that a electron becomes a photon is about 1%. But we send so many electrons across the tube that we still create a tremendous number of X-rays. So we've got this many electrons in 1 amp, but we never use a 1 amp exposure. 1 amp is 1000 MA, so one mass basically would be 1 amp. So that would be that many electrons. We more commonly use something on the order of 1 to 2, maybe 400 MA. So even if we only used 100 MA, then just knock one circle off of that, and you've got that many electrons. It's still an insane number of electrons. So the higher the MA that we use, the more electrons that we send. The more electrons that we send, the more photons we create. It's a predictable thing. If we double either one of our exposure factors, being MA or time, then we exactly double our exposure. If we double both of them, then we quadruple our exposure. In other words, if we had an exposure of 100 MA at 1 second, so that'd be 100 mass, and I changed my exposure to 200 MA at 2 seconds, that would be 400 mass. So if you double just one, then you double your overall mass, you double the number of photons that you create. If you double both of them, then it's a double-double. So when we change MA, what are the effects on each one of the following? Well, potential energy. What controls potential energy? That would be KVP. Potential energy being the measure of the speed of the electrons as they travel across the tube. The only thing that affects potential energy is KVP. So, no, MA has no effect on potential energy. What's kinetic energy? Kinetic energy is that speed that was built, or that is relatable to the potential energy that was created before the travel of the electrons. So it's the speed of the electrons. Well, what controls that? Well, KVP. Beam energy. What controls the beam energy? We're not talking about intensity. Intensity is mass. Beam energy is KVP. So does a change in MA affect potential energy, kinetic energy, beam energy? And the answer is no. Does it affect penetration? Well, no, it doesn't. The thing that controls whether or not something is going to be penetrated is KVP. Again, so it might affect the number of photons that penetrate through, but it's still going to be on a one-to-one type basis. So it doesn't control the percentage or the likelihood that an X-ray photon will penetrate through something, so it doesn't control penetration. Frequency and wavelength are, again, the energy of the X-ray photon, the individual X-ray photon, and those are both KVP. So what do changes in MA change? That's only the number of photons that you create. So how does that affect patient dose? And the effect on patient dose is direct. So you double your MA or you double your time at the same KVP, then your patient dose is going to exactly double. If you double your MA or double your time at the same KVP, then your image receptor exposure is going to exactly double. So it's predictable, it's relatable, you know exactly how much of a change you're going to make whenever you change your mass, regardless of whether you're going to change MA or time. You know exactly how much of a change you're going to make whenever you change your mass, and therefore most of the time that we want to make a technique change, we're going to use mass. So that was skipping ahead just a little bit and talking about mass overall. Mass occurs at exposure whenever the electrons are actually traveling across the tube. Remember, mass doesn't exist until we make an exposure. MA exists, filament current exists, but mass itself doesn't occur until we get exposure. So there's a word that you need to file away in your head and hang on to all the way through the registry, and that is reciprocity. The law of reciprocity. And what reciprocity is and what it means is to give and take. So imagine yourself using a saw cutting a board. Your arm goes back and forth and back and forth and back and forth. We've got motorized saws that do that, and what they call those saws are reciprocal saws. So reciprocal, they go back and forth, they go back and forth. There's give and there's take. There's push and pull. All right, so what that means here is that when we have an X-ray exposure and we manipulate our time, we can give and take and arrive at the same overall exposure in a lot of different ways. So if I make an exposure at 100 MA at 1 second, then what I have is 100 mass. But if I make an exposure at 200 MA at 1/2 of a second exposure, I still have 100 mass. All right, so that's reciprocity. The law of reciprocity means it implies that it doesn't really matter what your mass is. As long as your machine's shooting right, it doesn't matter what your mass is, mass should be mass. So providing your machine will allow you to make an exposure on small focal spot and large focal spot, if you can set a technique of, let's say, 20 mass at maybe, let's say 200 MA at 0.1 exposure on a large focal spot, and then you want to make that same exposure on small focal spot, then you should get the exact same mass. Mass is a measure of electrons, and it should be totally independent of the filament size that you use. Then if the machine allows you to make the same exposure on a large focal spot and a small focal spot, then the count of those electrons should be identical regardless of which focal spot you're using. So in that way, reciprocity means mass equals mass, and nothing else really matters. As long as the KVP doesn't change, then whatever mass you set, regardless how you arrive at that mass, should be the same. Just the count of electrons. So when to change mass, as long as you don't need to make a change in penetration or absorption or patient dose, if you don't have a pregnant patient or a pediatric patient where you want to cut the dose down, then most of the time you're just going to change your overall mass. And how you arrive at that mass is up to you, essentially. So your long exposure times often lead to motion, and sometimes motion is a good thing. So we talked about some procedures, some projections that we can use and utilize patient motion last semester, if you remember. Oblique sternum being one, transthoracic humerus was another. There are times when we want to see motion, or we want to utilize motion in order to better visualize anatomy, try to obscure some anatomy. And that's what we call autotomo. It's AUTOTOMO, autotomo. So it's tomography, which is part of computed tomography, but it's tomography, and tomography means to use motion in order to desuperimpose structures so that you can see them better. All right, so autotomo, and that is using motion to your benefit. Most of the time, motion's unwanted. So what we're going to talk about in the last section in this semester is sharpness of recorded detail. And the main thing that will destroy your sharpness of recorded detail, and it's something that you can't overcome fully because it's entirely up to the patient to prevent motion, is motion. So you can tell your patient not to breathe, but if the patient breathes, you can't do anything about it. You certainly can't stop a patient's heart from beating for a chest x-ray. You can't fully control bowel movement. So motion is not something that you can fully compensate for, but because of that, it's one of the main things that will destroy your sharpness of recorded detail. So most of the time, short exposure times are preferred to compensate for unwanted motion, especially in motion where the patient can't help themselves. So You've got voluntary motion, involuntary motion. If the patient can stop themselves from moving, then that's voluntary motion. Involuntary motion would be things, again, like your the movement of the bowels, and maybe your patient's got a Parkinson's or some sort of pathology where they can't stop moving. So it primarily helps with involuntary motion. Voluntary motion is best controlled with careful instructions. So if time gets too short, then you can have other issues as well. So again, back to quality control, our timers have to be accurate to within about plus or minus 5%, about plus or minus 5% of whatever you have set on your control panel. So you set 100 milliseconds, then it should be within a range of 95 to 105 milliseconds. Interesting thing occurs whenever we get to very short exposure times. At very short exposure times, that 5% could be much greater than 5%. So at reasonable exposure times, then your timer needs to be accurate to within plus or minus 5%. But once you get outside of that reasonable range, you get to a very short exposure time, or you get to a very long exposure time, then what you have is what we call, go back up here, reciprocity failure. So if you make an exposure with moderate MA and moderate time, and you want to eliminate some motion because the patient can't be still, so you maximize your MA and you minimize your time, then what you may have is a point of reciprocity failure. Your exposure time becomes so short that your machine can't respond adequately to how short a exposure time that you want to make. And it could be for a lot of different reasons. Maybe your image receptors aren't sensitive enough to make that exposure at that short a time, and maybe your timer initiation and extinction times are too short, or those times are too long to make the exposure begin and end on time. So in that case, you don't have mass equaling mass. What you have is a difference between your actual output and what you have set on your control panel. And in that way, you may introduce quantum model. Even though your mass may be good, because of the exposure time and reciprocity failure, you may introduce quantum model.